What happens to something when it falls into a black hole? Unfortunately, for us being three-dimensional spatial beings, it is impossible to visualize in three-dimensional space. However, it is clear as day in a two-dimensional universe. Two-dimensional universe being one where objects can go in one dimension, two dimensions, but not three dimensions. They're confined to the surface of two dimensions. And it is from this two-dimensional depiction that we will build the analogy into three-dimensional space. And once you see this, you can't unsee it. Now, let us introduce a hole into this universe. And we'll allow this path that I'm about to draw to be the path this little being takes. And it goes to the hole. Now, where is the only place left for that line to go and have it remain in this two-dimensional universe? Quite literally, the only place left is the other side. So that's the easy part, obviously, but now the harder part is drawing the analogy from that to three. First off, we have to take into regard, we're looking at a two-dimensional universe. That means it has no width. Even this paper has width. A true two-dimensional universe has no width. And if you ever read a textbook on general relativity, it's always describing things with two-dimensional manifolds, because there's really no other way to see any of this in three dimensions. But so we're dealing with a two-dimensional universe. That means it has no width. That means both sides are embedded within each other. That means a being on one, or any object on one side and any object on the other would be able to move around each other. Just like that. So now let's draw the analogy from that to three dimensions. So in three dimensions, to take that analogy and draw it to ours, that would mean that we would have an object. Obviously, me and this object in real life are on the same side of the fabric of space-time. Can move in three dimensions around me. Hope we can agree on that. But that would also mean that an object could be on the other side, and it would be invisible, by the way, but that would mean that an object could be on the other side and also move in three dimensions around me. So close, yet so far away. And as I'm about to show you, it is objects, matter that is on this other side that produces the effects which we see caused by dark matter. So if you're having trouble visualizing this, that there could be another side around us, I invite you to take a look at the two-dimensional universe. A being in this two-dimensional universe, if we told this two-dimensional being, hey, there's another side, this two-dimensional being would be like, what? This is the 2.5 dimensional visualization part of this video, more commonly known as the rubber sheet analogy for general relativity, where the curvature of this two-dimensional surface embedded in three dimensions will represent the gravitational interaction. More simply put, space-time tells matter how to move, matter tells space-time how to curve. Now this is just an analogy, but we'll see that this visualization represents the mathematics of general relativity perfectly, even for the region of negative radius. More specifically, the region behind the singularity of a black hole. So mass curves space-time, and that curvature is what objects follow as they travel. Geodesics. That's why things fall down. That's why the moon revolves around the earth, the planets around the sun, so on and so forth. Now, I'm not the first person to show gravity in such a way, but how would this massive object look from the other side? It would look something like this. Notice how it's invisible within the fabric of space-time, and all we can witness is the curvature of said space-time. By definition, dark matter. Now what do we notice when objects are on opposite sides of the fabric of space-time? there's a gravitational repulsion, an anti-gravitational interaction. And what is an anti-gravitational interaction responsible for driving apart objects in our universe? Dark energy. And now last, but certainly not least, how would an object get from one side to the other? At this point, I should probably say that the difference between a black hole and just a hole in the fabric is that a black hole is created when there's so much mass bending the fabric of space-time that it creates a hole. Just know that a hole like this, objects could go in and come back out. A black hole is just a one-way trip to the other side. So what type of matter from the standard model is producing these dark effects? Now you might have been wondering before what would happen if two objects on opposite sides occupied the same point. They would annihilate. So why is matter that's on the other side necessarily antimatter? Well, there's this thing called charge parity and time inversion, look it up if you must, where if two of those are inverted, then the third one must be inverted as well. While parity is inverted, why is time inverted? Well, picture yourself dropping a ball. Now play that mental picture in reverse. It would fall up. That's a time inversion. Now, since two of these are inverted, the third one must necessarily be inverted as well, and that is charge. And when charge is inverted, it is absolutely, without a doubt, antimatter. Then researching it a little bit more, I found out that there's a good amount of antimatter at the center of our galaxy, which is currently unexplainable. And what else is at the center of our galaxy? A supermassive black hole. The supermassive black hole at the center of our galaxy is without a doubt producing that fountain of antimatter. So I do got one little theory. The reason we don't see extraterrestrial life is because they figure this out. They go buck wild trying to produce antimatter from black holes, and they kill themselves off. Either that, or they don't figure this out, they get stuck on one planet and end up killing themselves off. Looks like either way we're fine. Alright, time to move on from this part. Oh, and speaking of time... Alright, so time to discuss time. What does all this mean for time? Well, space-time is one entity, and we've seen how the effects of space are opposite when two objects are on opposite sides. That's gravitational repulsion. So what would it mean for time to have the opposite effects when two objects are on opposite sides? And I'm assuming you just thought, does that mean time runs reverse on the other side? No. Objects on one side relative to objects on the other do not grow younger or anything like that. What it would mean for time is that the effects of gravitational time dilation are reversed. Objects on opposite sides experience gravitational time dilation than they would experience them when they're on the same side of the fabric of space-time. Meaning, the concept of gravitational time dilation is extremely easy to comprehend. Any clock, or object for that matter, within the presence of a massive object will experience time slower than one further away. Notice how the clock on the left, closer to the massive object, ticks slower than the one on the right, further away. So what would be the opposite effect of gravitational time dilation in regards to a clock on the opposite side of the fabric of space-time of some massive object? A clock close to an object while it's on the opposite side of the fabric of space-time would then tick faster than a clock that's further away. Notice how the clock on the left, closer to the dark matter / antimatter, is ticking faster than the clock on the right, which is further away. And this is the first thing I'll be proving mathematically within general relativity. The clock is attracted to a region where time ticks slower, and the clock is repulsed by a region where time ticks faster. The clock is a lazy fuck. So there's the equation for gravitational time dilation. Let's plot it out. Before we do that, let's get a quick review sesh. This little test particle is a positive radius from a positive mass. Now it's a negative radius from a positive mass. Now it's a positive radius from a negative mass, and a negative radius from a negative mass. That's done deal right there. That is a flawless mathematical description of everything I have just described. Where this right here is the event horizon of the black hole. I'll mark that. And also here is the singularity, a big bad singularity that I'm about to take care of here in a little bit. So what do we notice about this equation? This is telling us what we are on this side, what we already know. As we get closer and closer and closer, it takes more time to view a certain amount of time go by on a clock that's in the vicinity of the gravitational well. And also we notice as time gets slower and slower and slower, notice at the event horizon that it goes to infinity. Infinity amount of seconds to see any amount of time go by on a clock means that clock falling in has frozen in time. And now what do we notice on the other side, the region of negative radius that was previously uninterpretable? We see time getting faster and faster and faster as one approaches an object while on opposite sides. Remember how I showed in the 2.5 dimensional visualization? From a negative radius from a positive mass is on the opposite side. Next thing. Here's the event horizon, here's the singularity. Now I want us to notice something else about this graph. This spot right here and this spot right here are both 1 unit of measurement away from the singularity and from the event horizon. These two are 2 units away from the singularity and from the event horizon. Now I want us to notice something about these numbers, and this is the case for all these numbers across the board. They are inversely proportional to each other. All right, so why is that happening for spots that are equidistant on both sides? Is because those 2 spots are at the same point of the fabric of space-time, but just on opposite sides. If I have a massive object right here, and I'm this far away from it, let's say I would experience gravitational time dilation by 3. Now, if I'm on the opposite side in that same spot, now I experience it time by 1/3. This is due to the equivalence principle. And now, what do we notice about that singularity right there? All right. At the event horizon, it's infinity. What is the inverse of infinity? 0. The inverse of infinity, 1 divided by infinity, is 0. 1 divided by 0 is infinity. That means the event horizon and the singularity are at the same points of the fabric of space-time, but on opposite sides. So what does that mean? That means the singularity is the same point as the event horizon of the black hole on the other side. So what does that make it? That makes it the opening to the scarlet hole. I figured it out, I'm naming it. It's called the scarlet hole now. I'm saving the term white hole for the origins of the Big Bang. But it is the opposite of a black hole. A black hole, everything goes in. A scarlet hole, or a white hole as some of you know it, everything comes out of a scarlet hole. So if both the opening of the scarlet hole and the opening of the black hole are equidistant from each other, then that means we would want to see some sort of interesting behavior going on halfway between the two, right there. But since those numbers are imaginary, the only way to see that is to plot the imaginary numbers. I don't know what it means. Stephen Hawking didn't even know what imaginary time was. All I know is I like it. We got the event horizon of the black hole coinciding with the event horizon in the math, right? Now we got the imaginary numbers halfway through right there. And now we can plot the event horizon of the scarlet hole. Let's see. So that would give us something like this. You enter the black hole, go through, and pew, exits out the scarlet hole. That point halfway between is where the edge of the fabric of space-time is happening. So at this point, you might be like, wait a sec. I thought the singularity was a point of infinite density where all the mass is located at an infinitesimally small point in the fabric of space-time. So, physicists, mathematicians, everybody, why is that happening? Once again, we got the event horizon / singularity of the scarlet hole. We got the singularity of the black hole / event horizon of the black hole. So now let's get away all that superfluous material. We get something like this. Halfway between is the edge of the paper, if you will. Right there, boom, see that? That's where it goes over to the other side. So why is this right here appearing as a point of infinite density? Infinitesimally small point where all the mass is located. That is not real life. That is an error message. In essence, what you're doing is trying to take one side of the fabric and drag it through a hole onto a side it's not causally connected to. And you're trying to take one side and bring it in. And right there, within the interior of the hole, the metric is forgiving. It still lets you try to continue downwards with positive gravity. But then right before you get to that opening, it closes off to a point of infinite curvature. You're making gravity go inwards and inwards and inwards and inwards and inwards. Right there. And since we're only used to gravity working in one direction, you keep trying to make gravity fall inwards and inwards and inwards. At this point, the object is becoming antimatter and gaining anti-gravitational properties. That means what you need to be doing is taking the metric right there and going back out. See that? Going in, anti-gravitational effects acquired, back out. Not always positive, 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 because then you get that point of infinite curvature. The metric won't let you take it any further to the other side. If a black hole is eventually evaporating over time, then that means the stuff that fell inside of it is eventually escaping out into our universe somehow. Alright, so it goes a little something like this. Matter cannot be created or destroyed, only altered. You've probably heard that before. Meaning I can't just create matter from nothing, and I can't just delete it either. But I can alter it. Say, for instance, I took this lighter to this piece of paper. That would be altering it. I wouldn't be deleting the paper. I wouldn't be creating smoke. I would have just been altering matter. Now, when it comes to a black hole, it would appear that they are very much deleting matter from the universe. So things can fall into a black hole. The surface area increases when that happens. Now you can wait outside that black hole for all eternity. You will never see the comets or anything else that fell into it ever again. Not even the matter that formed it. Simply put, you could never acquire information from those objects ever again. So that's not the problem. The problem is that the great Stephen Hawking came along in 1974 and showed mathematically that black holes eventually evaporate and shrink over time until they disappear, not leaving behind a trace of what fell into it. It was also this discovery that put his name on the map. So the question is, where does all that matter go? It would appear as if matter has just been deleted from the universe. But the black hole information loss paradox says that the information about it is being deleted. We should always be able to acquire information from an object. Like if I were to burn that paper, I can acquire information from the smoke and see what it once was. So, the laws of physics say that information must always be preserved. Yet, it also appears to be the case that a black hole just deletes information. Hence, we have a paradox. Something is and something isn't simultaneously. Let me put that to bed now. Assume you and I are sitting outside of a black hole, talking on cell phones. Communicating with each other as all cell phones do through electromagnetic waves, which travel at the speed of light. So I decide to dip into the black hole, and we can still communicate with each other until I fall in. And that would be the last signal you ever received from me, the last bit of information. You would never be able to communicate with me ever again. You would never be able to acquire any information from me ever again. Even if I tried to send you an electromagnetic signal, it would never reach you. As you probably know, not even light escapes a black hole, and electromagnetic waves travel at the speed of light. Thus, if you can never communicate with me ever again after I've fallen into a black hole, then that means wherever the black hole is sending me after it's evaporated must also be a place you cannot communicate with me. If the other side of the fabric of space-time is a place you cannot communicate with electromagnetism, then electromagnetic waves would pass through objects on that side. If electromagnetic waves pass through objects on that side, and if they pass through me if I'm on that side now, that also means that visible light would pass through me while I'm on that other side, since visible light is an electromagnetic wave. Now, if electromagnetic waves pass right through me, then I am invisible. However, I still have mass, and I still warp the fabric of space-time. If I'm completely invisible, and yet I still warp the fabric of space-time, then I am necessarily, by definition, dark matter. Black hole information loss paradox resolved. The precise definition of dark matter achieved as well, without any assumptions to its existence within the argument. Doesn't get any better than that. So notice within the resolution of the paradox, I kept two things intact. One, information must always persist in our universe. Even if it's in a spot where it can't be acquired, it still needs to be in our universe. And the other side of the fabric of space-time is still part of our universe. And two, I had to account for the fact that information can never be gathered again, and hence, when it's on the other side, information cannot be acquired from it, thus it would appear as dark matter. And so last thing regarding that would mean that objects on opposite sides of each other appear to each other as dark matter. Yeah. There's one last thing I gotta say. The only three things we can acquire information from about objects while they're on the other side of the fabric of space-time are the only three things we can acquire information about from a black hole. That's its mass, spin, and charge. This is known as the no-hair theorem for black holes. These three become reversed when they're on the other side. Mass becomes negative, spin goes the opposite way, and finally, due to a parity inversion, charge must necessarily be reversed. And when charge is reversed, that means it's antimatter. Black holes make antimatter. And that would explain that currently unexplainable humongous cloud of antimatter at the center of our galaxy, ever so coincidentally in the vicinity of the supermassive black hole that is also at the center of our galaxy.